like tornado, something like that. Like I have done the modeling for this tensile characteristics in the tornado earthquakes. So I will go back again to refresh. So this is in the eruption forecasting section. So this seismicity transition prior to eruption, we have like common pattern. So this is the rest period. So during the background, you have like activities at volcanoes, but nothing is changing significantly. But when you detect increase in seismicity, most often, mostly you will find the high frequency events in the beginning. And then it will increase over time. And then just before the peak of the seismicity, or even after, you will have the low frequency events. And then after lower frequency, if you have a chance, you can have like tremor events, and then the eruptions. So that's the common pattern for seismic activities prior to eruptions. So the first stage high frequency, then low frequency, and then tremor, and then eruptions. But once again, so the high frequency, it's representing the magma pressure. So it's the beginning of the stress transmitted to the volcanic system. Then when this low frequency occurs, it means that the magma already hitting the shallower part of the volcano. The fluid fills the cavities. And then afterwards, it interacts with groundwater and it creates tremor. And then eruptions. Eruption can be in a form of fragmentations, if it is explosive eruption, or if it will not be, if it is not fragmented, then it will be an effusive lava flow. Okay, this is an example from USU in year 2000. You see that the VT earthquake precedes occur in the beginning, and then it was decreasing, but in the other hand, the low frequency was increasing here. The number is not so significant compared to the VT earthquakes, but the occurrence of LF earthquakes is important. If you identify that this LF events preceding, after the VT earthquakes, then there is a large probability that the magma or the fluids of magma or hydrothermal system already reached the shallower part of the volcano. And then here is the eruption concept. See, it can be in a matter of days, so it can be fast. So see that the increase only detected in March 27, 28, and then the eruption already happened in the end of the month. So it can be for only 4 days to have an eruption. But in other cases, like in Agung in 2017, it takes longer time. So as I said before, there is no time frame, similar common time frame. Because here at Agung, we see the increases in seismicity in VT earthquakes around there. And then we have increasing magnitude of earthquakes, but then it is decreasing, but eruption happened here. So we see clearly that the eruption didn't happen on the peak of the high frequency seismicity. So it takes 3 months for the volcano to erupt. It is different from the example from Busu. So, and for example, in Merapi 2010, we also see similar pattern here. We see VT events increasing over time. See, So months before the eruption, it was increasing like quite slowly, but then it's moving. So there is an acceleration in the last months before the eruptions. So and then it reached the maximum seismic VT seismicity of more than 200 events per day. So the alert level was increased at that time during the peak because it may be followed soon by an eruption. Because here, you see, after this, it moved to the low frequency events. So after the low frequency events occurred, and then days after erupted. So here you see that there is no events here. It is not, there is no events, but because there are so many tremor here, rock falls here, see, rock falls already recorded increasing here. And this rockfall has a higher amplitude than the low frequency event. So it is likely that during the same events here, the seismicity or the low frequency seismicity is increasing like this. But we could not detect this because the signal was covered by the rock falls. Oops, sorry. And also by pyroclastic flow. So the surface signals are more stronger than the low frequency events. So you see the biggest eruption is just here. So it really shows that after the high frequency swarm, we need to wait for the low frequency swarm before the eruption to take place. But we need to be careful because sometimes we don't see the low frequency events. But that's not because the events is not exist, but it is because it's covered by another signals that is much more impulsive or stronger in energy than this event. So even if we don't record the low frequency events during the seismic swarm or the VT swarm, we need to be careful. So that is why every time we reach the maximum size of the VT seismicity, normally we increase the alert level to the highest, because yeah, there is a uncertainty about the timing before the eruptions. It can be hours, like what happened in Uzu, can be days, like what happened in Merapi, but it can be months, like what happened at Agung. But you don't want to take risk of people's life, so we need to take actions here. So this is an example of Agung in other perspective. This is the RSAM. RSAM is the amplitude measurement over time. So this is the RSAM, and you see that we increased the alert level here, but then it was decreasing sharply. Then when it's come back to the background, so we decrease the alert level, but we decrease the alert level not to the second or the first, but to the third. It means that it still it can still be an eruption. So the eruption happened here. So the eruption in terms of number, so the earthquake counts is very low at the time. So now, in terms of frequency, also we also have done the automatic family classification using the RedPy code. You can find it freely in GitHub, and then it's already published just several months ago. You can check on the papers, and so we see that here. You see that the events, the VT events, was decreasing. You see, and then over time it was changing also the families, and then the families were changing over time. So there are families that are not exist anymore here during this transition period. So this transition is the transition between the high frequency to low frequency events. So here, one of the signature is the big magnitude 4.9 at 9 November. So if you seen, I will go back just fast to previous here. You see that the largest magnitude of earthquakes of VT here mostly will followed by the eruption. So that's one of the signatures of the signs that we need to be careful of. Okay, we will go back again. Okay, that's there. So the other part, I talk about the vocal mechanism. So the focal mechanism, we need to see also over time, if we could, if we have time. But normally, during the resting or the dormant period, the activity will be dominated by strike-slip mechanism VT earthquakes. So that's the, if you have intrusion, it will increase over time. But then the strike-slip mechanism will change into normal transition. Because before, in the beginning, the stress was caused by the deep magma movement that disturbed the local fault, original fault around, and that creates the strike-slip faults. But when it's already near or moving towards the volcano, then the focal mechanism will change from strike-slip to normal fault. So there are changes in vertical maximum stress, and before the maximum stress reached, we will always see this normal mechanism, focal mechanism, and then after the peak of the activity or after the eruption, after the volcano erupted, it is going back. So it will create the reverse focal mechanism. And then afterward, it slip again, going back to strike slip. Okay, now we learn about the transition from the seismic to co-seismic deformation. So if we see the seismic signals before, as I told you before, that when magma intruded or magma is moving from depth, there is an increasing stress. And this image, you see, is from MOGI model 2007. Sorry, there is no text here, but I will add. I hope you can see my text. You can see my text, yeah. I hope, oh, I cannot see my cursor. Sorry. Sorry, I cannot see my cursor. So, okay. In the beginning of the activity, you see, sorry, I cannot see my cursor. It's really bad. Sorry, I can't move my. Sorry. Okay, I hope I couldn't move the slides, so that's a problem. But in the beginning of the crisis, when the earthquake is increasing, what happened is that the differential stress, the stress is increasing, the strain is increasing. And at that time, you detect no seismicity. But if you have GPS stations around, you will detect deformations. And that kind of deformation is called elastic deformation. But at certain point, when you reach the threshold of the fracturing, so the maximum stress has already been reached. Sorry, I need to, okay, yes. Okay, here, in the beginning of the intrusion, you see that you may see no increase in volcanic earthquakes. So during here, and elastic deformation happening, and also the strain is increasing, the differential stress increasing. So here, the strain and the stress is increasing linearly at the same time. But when the differential stress reach the threshold of the fracturing, then it will move suddenly. And when the fracturing is happening here, then you will start to record seismicity. Then what happens is that this differential stress is like here, you see, it's kept at the same level. But the fracturing deformation is happening now. It's not elastic again, it's plastic or fracturing deformation. So at this point, you will see the deformation in your GPS or your EDM or tilt meters, but also you will see accelerating of seismic numbers. So that's the concept of moving from the aseismic to co-seismic deformation. So that's also important for us if we, for example, see deformation in our GPS data, but then we have seen nothing on the seismicity, then probably we are still here. But soon after the fracturing happens, what will happen is that it will followed by the increase in seismicity, the VT earthquakes in the beginning. Okay, this is the example. In 2010, eruption of Merapi. This is the long-term example of Merapi. You see that Merapi has a very good monitoring data. So this is the EDM data. So we see that the inflation already started at least here in 2009, in the month of April. Inflation, but without seismicity. You see that there is some seismicity, but very small seismicity. But the inflation continue gradual deformation. Here you see this is where the stress and the strain increasing linearly together. It is still in the elastic deformation steps. But then here it's moving. When you have like here, after the gradual deformation here, you see here you have increased significantly in event number, VD earthquakes number increasing. Then it's moving from the elastic deformation already to the fracturing deformation. And here the seismicity is increasing. And that follows the eruption. That is for the long-term example. And for the short-term examples is, for example, the Sakurajima from Tameguri and Iguchi, 2019. You see that before the inflation happened. See, the strain changing over time, and then earthquake swarm only started here. So then there is transition also from the elastic deformation to plastic or fracturing deformation, and then the explosion. So, and the last thing that we can do also with the seismic data, not the last thing, but in this presentation, is that how we assess the intrusion volume. Because we need to, when we give the, we increase the alert level, we need to guide, we need to know, or we need to assess how far will the eruption will affect people? How far from the summit crater? And to know how far, or to estimate how far, we need to know how much magma inside the volcano. So at that time, during the Agung crisis, we haven't recovered the GPS data because there was technical problem. So we don't have this kind of information during the crisis. But at this, after the crisis, we have this. And in fact, during the crisis, there were about 38 million cubic meters. So, but at that time, we also using the VT earthquakes, the seismic moments, as I told you before, to estimate the volume of the intrusion, and the numbers that we get was 39. So it's not that far. So it means that with seismic signals, if you have good networks and then you have good parameters, earthquake parameters, for example, like the magnitude, you have it all, then you will have a better estimate on the volume of the. So by knowing the volume, intrusion volume, it is good for the evaluation of the hazard, because if the volume is small, then we will not expecting a large eruption. But if it is a huge amount of magma moving towards the surface, then we have to evaluate this. So this is important for the evaluation of hazard. Now, the last one is the uncertainties before the discussion. So the uncertainty here is that what we see is an example. What we saw just now was were examples of success stories. There are many unsuccessful stories, because as I told you in the beginning, swarm of volcanic earthquakes is not always followed by an eruption. That's the key. So you see on this graph here, when the intensity of the monitoring parameters increasing, here is the decision window, where the public officials need to make decision. What assessment, the best assessment that he can have. But at that time, at the same time, there are at least 4 possibilities that will happen. It may be an eruption, which we probably wanted to have, or it can be back to sleep, so you don't have that, or it can increase over time and then fluctuate it for some times and then erupt it, or going back again to sleep. Okay, yeah, for that thing, oops, sorry. So the principal factors that affect the precursory and co-eruptive seismicity that also will, yeah, it's the age of the volcano. So the volcano type, the time since last magmatic eruption, the size of volcanic and hydrological system, the viscosity of magma, the petrology, temperature, gas content, and also the intruded volume. And maybe at this case, if you have not, for example, if you don't have like sufficient volume, it may go back to sleep. Maybe it's related to volume or other. So here, oops, sorry, I need to move this close. Okay, here it is similar with the previous slides. So there are 4 possibilities. The culmination in major eruption is the first possibility. But the second possibility is that turns to dormancy. And then other, yeah, this is the third. The second one is a combination in major eruption. But this is after a certain period of fluctuation. And the fourth is that you have an increase and then fluctuation, but continuously. And there are some examples here. Examples here are like Mount St. Helens in 1980 was the first, the examples of the first case. Mount Pinatubo in 1991. Merapi in 2010 is also this case. For the third one is like Campi Flegrei in Italy. It's increasing, but then decreasing. And for this one is like Rabaul in 1994, and also Agung in 2017. And also for this one is like the increasing and then decreasing, like mostly in like in caldera of volcanoes, like Yellowstone, Long Valley, and in Indonesia recently we have Toba, Toba swarm. This maybe like this scenario. So the key words is that even though we have studied the volcanoes with many sophisticated technology and monitored closely 24 hours a day, real time, it is still impossible until now to determine the outcome of the unrest at most of them. So most of them are still with high uncertainty. So when we go back again to the first slide, can we really forecast the volcano? Yes, we can. We can, but with uncertainty. So that's here as a discussion. So I want to discuss about the model. So because in the end, what you are trying to do with seismic data is that you are trying to understand what happened during the actual model for each volcano, because one to other volcanoes may be different, or even one volcano to itself in other times may be different. So this is important to estimate the state of volcanic activities. And even if we only have, for example, seismic data, and we don't have other data, we could already start to make a model with reference from analog or simulated make a model. Because if you always want to have a perfect or complete data set, then the model will not exist at any time. So a conceptual model. Can you hear me?
Yes.
Okay.
Yes, I can.
Okay. There are several models. So for example, I will show you a conceptual model may be changed over time in accordance with observational data. So here I showed you what one of my publications during the Agung crisis. In the beginning, we thought, oops, sorry. With I need to annotate. We thought that the processes was like this. So this was the first model that we used to interpret the crisis in the beginning. In the beginning of the crisis, we used this model. But after we have more data, we have insights from INSAR and also GPS data. we got another information that this might not be this kind of model. So we change our model. We change our model to this kind of model. So we think that there was a dike intrusion. So that is why in the paper, we mentioned that in the beginning of the crisis, we have this kind of model. But then after, we change our model to this model, because this is more consistent with other parameters. Other parameters means the remote sensing data, the GPS data, and others. So, but at that time, that was a conceptual model. So we don't know exactly what is inside the volcano at that time. So we continue our research, and in the recent publications from the tomography and also from the analysis, it shows a similar result to our model. So that means that this model is a confirmed model now, based on this how to say, based on this data, field data. So this is actual data, not a model anymore. Okay, I think I have finished my time now. I would like to say thank you. And you have questions, we have 15 minutes from now. And I put you my email address. And if you would like to ask me in more specific questions or others, or if you want to collaborate, you can always send me an email. Thank you.
Okay, thank you, Pak Devy, for the interesting presentation here. And we have several questions in the chat. The first one is from Vanessa. So the question is, if there is magma lateral migration in the brittle zone, it will be detected on the stage 3 as proximal VT or in the stage 4 as tornillo?
Okay. If there is a lateral migration in the brittle zone, it will be detected. When you see, first we will see the seismicity. I mean the seismic event type. So and for example, if we detect this as like a shallow VT or proximal VT, that's the stage 3. But that we need to check with the frequency content. We need to check the onset of the earthquakes, whether it is impulsive or emergent. For example, if it is an impulsive high frequency event, then it will be detected as the third stage, as proximal VTs. But at this stage, you see that it can be accompanied already by explosions. Some explosions happen during the third stage. So and if it is a stage 4, normally you can have like proximal VTs, but it's happening repetitively. So it's like a drum beat, you say, like regularly spacing events. That could happen also. That was in the late stage at the 4th, but not as tornillo, of course. If it depends, once again, I said to you, it depends on the frequency content. If the frequency content is low, then if it is in the 3rd stage, it will be in the form of low frequency events. But if the high frequency events, if it is high frequency event, then it's the proximal VTs. But in the late stage, you will have like repetitive VTs, or you can have large magnitude of low frequency. So not the number. for the low frequency events, so I need to point out this is very important for you, that for the high frequency events, numbers is important. Numbers of events is important. But in low frequency, in the low frequency events, number is not important, but the duration is the most important one. So that's why here, if you want to, how to say, to interpret this, you need to see which kind of events. So if the lateral migration is, if it is the lateral migration is in the form of fluids that is resonating the a crack, lateral crack, for example, it can be in the form of tornado. You can have that kind of events as well. But if the lateral migration is in the form of like a dike intrusions, or going up in following cracks or conduit, then it could be a proximal VT. So, and the second question is, could we expect a different pattern in monogenic volcanic fields where there is not a main volcanic edifice? Yeah, it's possible. Different pattern, as I told you before, that there is no, what I showed you is that common pattern. Doesn't necessarily say that all will be similar, but that common patterns could help us to understand in which stage of the activities we are in. So yeah, I think that's my answer for Vanessa. If you still have questions, or if my answer is not clear, please, you can ask again.
No, that's all. Thank you very much.
Thank you, Vanessa.
Okay. And the next question, Pak Devy from Muhda Cimote. Hello, fantastic lecture so far. He had two questions. I know of few recent studies from Iceland that have linked earthquake frequency to magma viscosity and then to volcano explosivity. Can we instead directly predict volcano explosivity and volume of magma chamber based on seismic data analysis?
Okay. Okay. The first question is about the. Okay, I'm laughing reading the second question. Okay.
Okay.
Sorry. So the first question about yeah. In fact, can we instead directly predict volcano explosivity and volume based on seismic data analysis? Yeah, as I showed you before, that is a possibility, clearly a clear possibility. So if we manage to calculate, for example, to calculate the magnitude of each VT events, and then we can have certain, because it is directly proportional to the intruded volume, then we can have the volume of intruded magma based on the seismic data, of course. And for the studies from Iceland that related the earthquake frequency to magma viscosity, then to volcano explosivity. Yeah, you see, as I told you before, that maybe it is related to the long period seismicity or the low frequency seismicity. So in this type of seismicity, you see that there is an analysis called the complex frequency analysis, that you analyze the complex frequency means that you analyze also the beside the frequency, but also the Q factors. And these two parameters are important because it is related to the acoustic properties of the cracks. So, and of the fluids, sorry, the acoustic properties of the cracks, and also the properties of the fluids. What I would like to say that it is possible for us, using this kind of analysis, to see whether the cracks is growing or decreasing. So the changes in frequency reflects the changes in the acoustic properties. So you say it is very simple. It's like glass. So if it is empty, then you have it will give you a different tone with the glass that is full of water. So that's what happened also at volcanoes. When you have larger or bigger or inflating cracks, then you will have certainly a decreasing frequency. So in some papers, we've seen that decreasing frequency of long period events may lead to eruptions, because you see that there was an inflating or volumetric changes, increasing volumetric volumetric changes, and then can followed by eruption. The examples are numerous, yeah? So many. At Kelut in Indonesia, for example, it happened like that in 1990. Prior to the eruptions, you have decreasing dominant frequency of low frequency events. And then the coda part of the low frequency events of the Tornio, for example, related to the type of the fluids. You can read the paper from Bernard Chouet or Kumagai, Hiroyuki Kumagai from Japan. They extensively study this kind of study. So that's also my study. So I have also did the analysis for some volcanoes in Indonesia. So and we could forecast what type of eruption it could be based on that data. So together with volume, and with that we can see that if the volume is large, for example, you estimate that the estimated volume is 100,000 or 100 million cubic meters, then you would expect large eruptions, right? And then from the analysis of the frequency of the long period events, you see that from the coda part, the analysis, it was mainly from like ash, laden, or something like that, or rich in gas. For example, like in Merapi, there is already a publication that the low frequency content prior to the largest eruptions is a very short duration, long period events. But that short duration indicated the high content of CO2. So it reflects that kind of fluids. So the CO2 at that moment. So, and certainly that will be helpful because sometimes you don't have gas data on site. You only have seismic data. But this kind of event can help you to estimate. But again, it depends also with the volcano. Sometimes that kind of events didn't occur at all. So, okay, number two, apart from MS Excel, what are the most commonly used software for seismic data analysis? So there are many. I rarely use MS Excel except for calculating the volume. Mostly I used OBSPy because we most often use OBSPy or Python because that's the we have used. I personally have used Python since I think 2009, so 12 years from now. And I will encourage you also to use Python because there are already many packages exist in GitHub, and so that we don't have to make anything from scratch all time. Okay, thank you.
Okay, so maybe another question for Pak Devy here. Oh, okay, from Aldo and Rizka here. From Aldo P, is the classification of seismic events the same worldwide, or are there any changes or modification in some countries, for example, with the tornillo term?
Yeah, so in fact, for the classifications, the unified, I mean, not unified, there is no single similar classification around the world, but in fact, that's not the main importance. The most important thing is to understand the physical processes that happen inside the volcano. So when you can estimate what happened, then any classification, even if it is this different name, then you can still estimate the processes. Like I showed you before, Minakami, Latter, and also McNutt and others, and Zobin, they have different terms, but the physical processes is similar. So, for example, not only in Indonesia, not only in other countries, but in Indonesia itself, we have like different classifications for I mean the name of classification of earthquakes for different volcanoes. For example, in Merapi they have multi-phase earthquakes that in Sinabung we called it hybrid events, but both are the same events. So that's not the I'm seeing changes in the classification in terms of the name is not so important. So the most important thing is that you know exactly the physical processes of this event. And for the tornado is considered as low frequency events, yeah, but different from other volcanoes, from not other volcanoes, different from other low frequency events, because you see that the classic low frequency events, they have emergent arrival onset of the emergent onset of the signal, and then it keep increasing and then increasing, but sometimes it's also oscillating. But for the tornado or the long period events, you see that the slowly decaying coda is nearly almost linear. So that is why we can model that that decaying coda to assess the type of fluid inside a crack, because the oscillations that caused by these events may differ if we have different type of fluid. So that's for the tornado term. So I think there are many in other part of the world, they have different classifications, but in general, you will see like people will say will have similar perspective on high frequency and then low frequency and then tremor and then explosions. So something like that. That's in general. Okay, and assess the hazard. It's should I answer this? Yes. Hello.
Yes. For Rizka questions.
Okay, Rizka question. How assess the hazard? Maybe limitation lower extent. Okay. Yeah. For this kind of event, for example, unexpected event like in Krakatau 2018, it is difficult to assess the secondary hazards. Because what we monitor at volcanoes is volcanic activities. We don't have sensors at that time to detect the tsunami, for example. The landslides that happen didn't have a clear signal. If you find it, retrospectively. So it is rather difficult. I think, I don't know if there is an example that if we could see changes in prospective analysis, not retrospective, to see if there will be a collapse before an eruption. Oh, sorry, before the collapse. And so this kind of hazard is difficult not only for us, but I think it's for most of people, because this needs not only volcanologists who work here, because our main concern is magmatic processes that, volcanic processes with of course evaluating hazards, but something like the collapse, it is really difficult, because you see nothing before the collapse. I mean, you may see something, but it doesn't necessarily become the direction that it will certainly be collapsed. Like the one in Mount St. Helens in 1982. You see that there is a bulge coming out, but who will think that there will be a collapse of that ledge? So we may see something, but we cannot really predict the outcome of what will happen. So that's difficulty of, and what kind of assessment that we do? Normally we do the probabilistic assessment using the event tree techniques developed by Newhall et al.
Okay. Okay, maybe that's for the last questions for today. If you have any further question, maybe you can send email directly to Pak Devy here. So thank you for your great lecture today, Pak Devy, and we really learned a lot from you. Maybe before I end this virtual course, I would like to announce something for the students. There will be an email sent to you for assignment for these virtual courses, and for the detail of the assignment, you could check directly to your email. So maybe I will conclude today's virtual course. Thank you once again, Pak Devy. So this is the end of the second day of the virtual course. Stay safe and stay healthy, and see you tomorrow at the same time. Thank you for today.
Thank you, everyone, and have a successful course until the end.
Okay, thank you, Pak Devy.